So let's get back to our survival story. You've created fire through a combination reaction. Now you feel warm and nice. You've also managed to cook some food with the same fire for yourself. It may be a nice barbecue to keep you going for a while. While you take a nap, your body is actually working really hard to break down the food that you've eaten. All the complex food molecules are getting broken down into simpler food molecules like glucose. And that's not all. When you respire, the glucose gets converted into energy in the presence of oxygen. And that is exactly the equation that you just saw. That was your glucose, which was C6H12O6 in the presence of oxygen, goes ahead and gives you carbon dioxide and water, and energy is getting released. Energy over here, you may note, is not in the form of fire, but it is in the form of ATP molecules. And we will definitely get into that in the chapter on respiration. And that's the beauty of chemistry in your own body. Now, your slumber is interrupted by the roaring clouds above you. And before it starts pouring, you need to get yourself some shelter. We need some building material. Being a smart student that you are, you immediately realize that you will need concrete. How can you make concrete on this island? Seashells. Seashells are abundant. Powder them and you have calcium carbonate, because seashells are actually made up of calcium carbonate. You heat this powder and you end up with calcium oxide. This is also known as burnt lime or quicklime. This is one of the main ingredients for making cement. This mixed with volcanic rocks, as volcanic rocks are rich in magnesium, will give you cement. Throw in some pebbles and sand and you have concrete. And there you're ready to build your house. So what was important in this chemical reaction was calcium carbonate was breaking down into calcium oxide and carbon dioxide. To represent this chemical equation, CaCO3 is going to go ahead and give you CaO and CO2. This kind of reactions have a special name to it, and the name is very obvious. It is known as decomposition. In this reaction, you can observe that a single reactant breaks down to give you simpler products. This is a decomposition reaction. To generalize such an equation, we can represent it like this. AB is going to give rise to A plus B. That is, single reactants give rise to multiple products.
Now that you've understood this kind of a reaction, we will look at some more examples so that decomposition becomes very, very, very clear to you. Now, let's consider the decomposition of ferrous sulfate, okay? The representation is like this. 2FeSO4.7H2O will give you Fe2O3 plus SO2 plus SO3 plus 14H2O. Now, since it's decomposition, you need something to be given as a trigger for this reaction, right? In this case, it is heat. Now, let's perform this experiment to actually see what happens. What you need to do is take some ferrous sulfate crystals in a boiling tube, and don't forget to note the color of the ferrous sulfate crystals. They're green in color, right? Now, heat the boiling tube over the flame of a burner till you can observe a color change. And what is the color of the crystals after heating? And why is that happening? This is what we need to understand. So what can you actually observe? 1, the green color of the ferrous sulfate crystals are changing to a black residue, and this is ferric oxide, represented as Fe2O3, which is a solid. Then you can also see fumes coming from the mouth of the test tube. This is burning sulfur from sulfur dioxide and sulfur trioxide. Now the odor would be similar to the smell you will get after loads of firecrackers are burst during Diwali. And finally, you can also see some droplets at the mouth of the test tube. This is water. Example 2 is the decomposition of lead nitrate. So what we'll do is we'll actually heat up lead nitrate and see what happens. Lead nitrate will decompose into lead oxide, nitrogen dioxide and oxygen. To represent that in an equation, PbNO3 twice when heated will give you PbO plus NO2 plus O2. And I'm sure that you already observed that this is not a balanced equation. So let's just balance this for practice, okay? So how do you go about doing that? We're going to balance this using the shortcut which we discussed earlier. Okay, so what we'll first do is to put the coefficients A, B, C and D. And let's equate the number of elements on the left and the right hand side. So first let's consider lead first, okay? So if you consider lead, you get A is equal to B. Then next, if you consider N, nitrogen, you will get 2A is equal to C. If you consider oxygen, you get 6A is equal to B plus 2C plus 2D. Now, what we're going to do is, if you remember what I taught you last time, make A equal to 1. Why? Because that's the largest compound, right? Lead nitrate is the largest compound. So make A is equal to 1. then what do you get? When you substitute in these equations, you'll get A is equal to 1, B is equal to 1, C is equal to 2, and D is equal to half. Don't worry, you're not stuck. Okay, when you get a fractional value, what you simply need to do is to multiply it so that that fractional value becomes a whole number. So multiply it by 2. Multiply everything by 2. So you get A is equal to 2, B is equal to 2, C is equal to 4, and D is equal to 1. So what is a balanced equation? It is 2 PbNO3 twice, giving you 2 PbO plus 4 NO2 plus O2. Add the physical states and your equation is balanced. Now, let's perform this experiment in a lab and see what happens. What are we doing? We are heating lead nitrate powder in a boiling tube. You'll observe that brown fumes of nitrogen dioxide are being given out, and to detect oxygen, ignite a splinter, put it off, and bring it to the mouth of the test tube. It will reignite. It's not magic, it's oxygen. The third example for decomposition is the electrolysis of water. This is something you might have actually performed in the lab. Now, electrolysis of water, what do? Take a beaker, fill it with water, add some salt to it. Why do you do that? To make it conductive. Now, drop a battery into it. What is happening is that an electric current passes through the water and bubbles of gas get formed at both the positive and the negative ends of the battery. Now, how do you verify what is being formed? Take 2 test tubes filled with water, invert them over the positive and the negative ends. These bubbles will displace water in the test tubes. And notice one very, very important thing here. The volume of the gas collected in both the test tubes are different. Why is that? In fact, at the cathode, you can see that the volume is higher and this contains hydrogen. And that's correct because in water, you have 2 molecules of hydrogen for 1 of oxygen. And at the anode, you get oxygen. Let's do one more. There are so many decomposition reactions that I just need to discuss at least one more. Okay. So if you expose silver chloride to sunlight, which is white in color, it will turn gray. Why? Why does this happen? It is because of the decomposition of silver chloride into silver and chlorine by light. And how would you represent this in an equation? 2AgCl in the presence of sunlight will give you 2Ag plus Cl2. Now, silver bromide also behaves in the same way, and in that case, you can represent it as 2AgBr in the presence of sunlight will give you 2Ag plus Br2. Put the physical states. Do not forget that. There is a very, very interesting use for this reaction. You may know this. They are used in black and white photography, and I'm going to give you a little task. You need to go and find out how that exactly happens. Now, decomposition reactions, as you must have observed, again and again, need energy in the form of heat, light, or electricity to actually break down the reactants and give the products. Now, I hope decomposition is very, very clear to you.
Wood getting converted to coal is also an example of a decomposition reaction. While you wait for someone to rescue you, you paint your house. You must be thinking, crazy teacher, what is he making me do? But listen to me, you have to paint your house. For the sake of chemistry, you need to paint it. Focus now. To paint your house, you will require slaked lime. How do you get that? If you mix calcium oxide that you obtained after the crushed seashells was heated with water, you get calcium hydroxide. And this can be shown in an equation like this. CaO plus H2O is going to give you CaOH twice. And the CaOH twice is what is known as slaked lime. And this is what is used to paint your house. By the way, the chuna, that is the white powder that you get when you rub the wall, is exactly CaOH twice. And this, you must have already recognized, is a combination reaction. Also, calcium hydroxide reacts slowly with the carbon dioxide in the air to form a thin layer of calcium carbonate on the walls. The calcium carbonate is formed after 2 or 3 days of whitewashing, and this gives you the shiny finish to the walls. And this equation can be represented as CaOH twice plus CO2 is going to go ahead and give you CaCO3 plus H2O. And what a cycle! CaCO3 when heated becomes CaO, CaO when you add water to it becomes CaOH twice, and CaOH twice which mixes with carbon dioxide and gets back to CaCO3. Now that you've painted your walls with slaked lime, tough work. I'm sure you've got dirty. You will definitely need to wash yourself. For this, you will need to create soap. How do you create soap? Take plant ash, which will contain K2CO3, that's potassium carbonate. Mix it up with slaked lime, that's CaOH twice, and it will give you calcium carbonate, which will precipitate out of the solution. The liquid part of the solution will contain potassium hydroxide, which you will mix with fat and you will end up with soap. And you can go ahead and take a nice dip in the gushing stream nearby. To represent these chemicals in the everyday language, plant ash, when mixed with slaked lime, will give you powdered seashells and plastic potash. In the chemical equation, K2CO3, which is plant ash, plus CaOH twice, which is slaked lime, is going to go ahead and give you CaCO3, which is crushed seashells, and KOH. When mixed with fat, you will get soap. And what we just saw was the next kind of reaction known as the double displacement reaction. And this can be represented in general as AB plus CD, giving you AC plus BD.
Now that you've understood in the best possible way a perfect example for a double displacement reaction, let's look at some more examples to actually understand why the reactions work this way. So what I'm going to do is take some sodium sulfate in a test tube and mix it with barium chloride solution, okay, in another test tube. You will observe that a white substance that is insoluble in water is formed. And when you get an insoluble substance, it is called a precipitate. And in this case, the precipitate is barium sulfate. So to understand this equation is going to help you understand it really well, okay? So Na2SO4 plus BaCl2 will give you BaSO4 plus 2NaCl. So in solution, the reactants separate out, they become ions like this. So it becomes 2Na plus SO4 2 minus, Ba2 plus and 2Cl minus. What exactly happens is Na and Cl come together like this, Ba and SO4 come together like this, and why that happens actually is because there is more attraction for Na and Cl in solution. So they can actually come together. Reactions in which there is an exchange of ions between the reactants like this is called a double displacement reaction.
Near the stream, you will find a mystical blue water. You are very curious to see what this is and you collect this in an iron pot that is lying nearby. You see that after some time, this mystical blue water starts to pour out of this iron vessel, which basically means the blue water has eaten in or corroded into the iron pot. Now let's try looking at the reaction that occurred. The mystical blue water is copper sulfate. What happens here is iron or Fe is converted into FeSO4. Hence, it looks like it is corroded or the copper sulfate solution has eaten into it. The basic reaction can be represented this way. Fe plus CuSO4 is giving you FeSO4 plus Cu. The SO4 minus 2 ions feel more comfortable with iron over copper, and you'll understand why this happens when you learn more about it in the periodic table. And this kind of reaction is called a single displacement reaction, and this can be represented as follows. A plus BC is going to give you AC plus B. And if you've still not understood, take a look at this displacement.
Now let's see what happens when we put iron nails in copper sulfate solution. You have a real example. Now let's look at it, technically. Take 2 iron nails and dip them in copper sulfate solution. What do you see? After a while, you'll see a deposit of copper on the iron nails. If you want more examples, the same thing actually happens when you dip lead in copper chloride. And how will you show this in an equation? You have Pb plus CuCl2 giving you PbCl2 plus Cu. The same thing also happens with zinc. But why does this actually happen? It's because zinc and lead are more reactive than copper and they displace copper from its compounds.
Finally, it's time to get back home. To get back home, you will need to signal the passing ships or aeroplanes to come and get you. So you know what you need to do. You will need to create fireworks. And this will require, explosive powder. Charcoal, sulfur, and potassium nitrate or saltpeter is the ingredients that you will need to have to create this explosive powder. We already have charcoal. We scrape up sulfur in an elemental form from the same volcano where you got volcanic rocks. So what about potassium nitrate? A major source of potassium nitrate is either the deposits of crystals from cave walls or the accumulation of bat excreta in the caves. Extraction is accomplished by immersing the excreta in water for a day, filtering and harvesting the crystals in the filtered water. Be sure to mix them all separately because if you don't, you may even blow your fingers or even you may blow out your whole hand. The equation, if I have to go ahead and represent it once more, carbon for potassium nitrate plus sulfur is going to give you carbon dioxide, nitrogen and potassium sulfide. In its chemical form, 3C plus 2KNO3 plus sulfur is going to give you 3CO2 plus N2 plus K2S, and finally you get the bang. What is happening here is a reduction and oxidation reaction, and let's understand exactly how this happens. Electrons to chemistry is the same as money is to a capitalist. It's all about who has it, who wants more of it, who can share it, who can lend it, and what they are ready to get more of it. In fact, when electrons move from one atom to another, there can be a lot of exchange of energy, and this kind of reaction is known as a redox reaction, or a reduction and oxidation reaction. And what's up with those words? Reduction is making less of something, and oxidation has to do something with oxygen. Well, most of the time, but not always. Actually, these are super terrible choices to what is happening in a redox reaction. But for a matter of fact, we are just stuck with them. Actually, reduction is when a substance gains electrons. Yes, it gains electrons. It's exactly opposite of what reduce means. I really wish scientists could have named these things more appropriately to make our lives simpler. You know, when you come to think about it, it must have actually made sense to call these reduction reactions, because in those days, chemists would make pure metal by heating or smelting their ores. And they noticed that these substances would become lighter when smelted. So I guess it was but natural to say that these substances were being reduced as they were getting smaller. Our good friend Antoine Lavoisier noticed that oxygen gas was leaving when he heated the metal. What he did not know was actual chemistry was involved here. Oxygen is essentially the oxidizer because it pulls away electrons to make itself more stable. This is why you will require oxygen to burn fuel. What oxygen does here is to pull away the electrons and release energy. That's the same reason why we breathe oxygen, because oxygen absorbs electrons in the mitochondria to release energy and to go ahead and create your ATP molecules. We will learn about this in greater detail in the chapter on life processes. Anyway, now that we understand that reduction and oxidation is all about electron transfers, and to keep these names straight, I rely on a phrase which is oil ring. Oil basically is oxidation is losing electrons and reduction is gaining electrons. You've got to know this stuff because it's everywhere. Your energy obtained to do all the activities is because of redox. The plant synthesizes food from sunlight and carbon dioxide. That is redox. The battery powering the tablet that you're holding, that is redox. Fire, redox. Rusting of iron, redox. Rancidity of oil, redox. So reduction and oxidation is all around us. You know why your bag of chips are flushed with nitrogen? That is to prevent the oxidation, which will essentially cause staleness of the chips, or this is known as rancidity. What about rusting of iron? You might have seen that iron is shiny when they are new, but they get coated with this reddish brown powder when they get exposed to water and oxygen. This is also an oxidation reaction, and it is known as corrosion. And a huge amount of money is spent every year on the replacement of corroded iron. I'm going to go ahead and give you a task to the curious minds. Hey, have you seen this iron pillar in Delhi, which was constructed way back in the 1300s? It has been exposed to water, oxygen, and the atmosphere, but it hasn't corroded. How is that possible? Okay, now since electron swapping is the name of the game, here, when we are talking about the redox reactions, it is important, essential, critical, and absolutely necessary to track the changes that the number of electrons are happening. In these chemical transactions, one person is going to gain electrons while the other is going to lose them. Let's look at a really simple equation. You have hydrogen gas, which will combine with fluorine gas to give you hydrogen fluoride. If you look at the electron transfer, you will see that hydrogen is the element that loses the electron and fluorine is the element that has gained the electron. Hence, hydrogen has oxidized and fluorine has got reduced. A simpler way to look at it is that if a substance gains oxygen or loses hydrogen during a reaction, you call that substance as oxidized, and if a substance loses oxygen or gains hydrogen during a reaction, it is known as reduced. The first reaction that you studied, where you created fire on the marooned island, is when carbon was getting oxidized to form carbon dioxide. That is, carbon plus oxygen is going to give you carbon dioxide. This is an example of an oxidation reaction. If you take copper powder and heat it up in the presence of oxygen, you will see that the copper color is changed into a black residue. What is happening here? The surface of copper powder becomes coated with a black copper oxide. Why is this black substance formed? This is because oxygen gets added to copper and copper oxide is getting formed. And this can be represented in molecular form as follows. 2Cu plus O2 in the presence of heat is going to give you 2CuO. And if you want to convert the CuO back into copper, what you have to do is to pass hydrogen gas over it. The black coating on the surface of the copper oxide turns back into copper by a reverse reaction and copper is obtained. That is, CuO plus H2 in the presence of heat gives you Cu plus H2O. Now, if a substance gains oxygen during a reaction, it is said to be oxidized, and if a substance loses oxygen during a reaction, it is said to be reduced. During this reaction, the copper oxide is losing oxygen and is being reduced, and hydrogen is gaining oxygen and is being oxidized. In other words, one reactant gets oxidized while the other gets reduced during a reaction. Such reactions are called as oxidation reduction reactions or redox reactions. And finally, in our Big Bang equation, electrons are moving from one molecule to the other to form the products. Some movements consume lesser energy, and the extra energy is what gets released as the bang.
There's one final set of reactions you need to understand. What happens when some of the reactions give out heat, and what happens when others absorb heat. If a reaction gives out heat, it's called an exothermic reaction. And if it absorbs heat, it's called an endothermic reaction. You have exothermic reactions happening inside you. When glucose gets oxidized, energy is given out and is used to mint our energy currency, ATP. Let me put this in a graph so that it will become very, very simple for you, okay? So you must have actually noticed that we have instigated some reactions to happen. That instigation was normally heat. And this is done because reactants are usually stable in their own form. A small push or a trigger is needed to get them going and getting them to react. This energy that is given is called activation energy. After this, the reaction becomes spontaneous, goes ahead and forms different products. Now, two things can happen. One, products can be at a higher energy level than the reactants, which means that they have absorbed the energy. In this case, the reaction is called an endothermic reaction. And if you ask me for some examples of an endothermic reaction, the biggest example would be photosynthesis, a process by which plants are capable of the magical process of making their own food. This is an example of an endothermic reaction. Now you can show this in an equation as carbon dioxide plus water plus energy in the presence of chlorophyll, giving you glucose and oxygen. Now, if products are at a lower energy level than the reactants, this means they are giving out energy, and this is called an exothermic reaction. Examples: digestion, respiration. And if you want to show respiration in an equation, you have C6H12O6, that is glucose plus oxygen, giving you carbon dioxide, water and energy. Some more examples: burning of a candle is exothermic, burning of natural gas is exothermic. Now, how would you show burning of gas? In an equation, CH4 plus oxygen giving you CO2 and H2O. Even decomposition of vegetable matter into compost is an example of an exothermic reaction. The explosion that saved you and brought you back home safe and sound. As a matter of fact, all explosions are some of the most violent exothermic reactions.